Okay, continuing on the Denon DR-M44 on the idler tires that I received the last time that were the right ID and OD, but the too thick, incorrect thickness. So now I've received the new tires from my vendor, but and these are the right thickness and ID, but they are not the right OD. And I spent many hours online looking for the correct measurements and everything that I could find, and I have sources on this sort of thing all over, and I couldn't find anything. So I'm faced with a few different options. One is to make a new hub, a new pulley from brass, or even Delrin was my first thought. And my other option is to put a spacer. So let's measure these up and see what I need to fabricate. This is the original tire that came off, and it's going to be in the 16.8 something millimeter range. It's a 17 millimeter tire. And the ones that I received are 16 millimeter tires. So I'm lacking a millimeter, or half a millimeter on the radius. So I'll put it on the pulley and measure it again in the hopes that maybe it stretched it out and I gained a little bit. But I really didn't. And I want to show why this is important in this particular deck. All right, I'm in focus now, and I can show the travel limiters. Those two little vertical forks that stop the rotation of that idler pulley. I'll get this set up here. Try to get I'm zoomed in as far as I can get. Try to get this lined up so that I can try to show what I'm seeing and what I'm kind of feeling. Okay, so there's the travel limiter. I get the springs put on here so that it simulates the actual force on the wheel and the tire. And I'll try really hard to get a couple of camera angles and show why I believe this is a problem, meaning the reduced diameter. Okay, that's max zoom. That's as good as I can get. And that is the position of the motor pulley, the driver pulley. And there's the travel, normal travel. I've got to get the rest of the components in line here. Need to block up those brakes so that I can simulate it correctly. I'll just stick a tiny screwdriver in there and lock it up. Okay, brakes off. And there's quite a bit more play in this than there would be if it were, you know, correctly positioned and the motor and everything in place. But so there's what I'm faced with. The pivot back and forth. On the real pulley, which is just barely visible, but I think you get the idea. This is really hard to do for a camera. It's not that hard when you're just doing it, but when you're trying to do it for the camera, it's a whole different animal. So of course there's no way I can, you know, show what I'm feeling and what I'm seeing all together, but my impression is that the diameter reduction on that is okay. It would work right this minute. But as that tire wears down, and they do wear down, there will be a point where it no longer can make sufficient contact with the table pulleys. And it's not that much, like I measured and showed, but it's enough that it just won't work. I've got to come up with a solution for it. I'm lacking something in the area of maybe 50 thousandths. It's very little that I need to come up with. But I have to come up with it somehow. There are different options. I can machine a brand new pulley out of Delrin brass. I can put a spacer in there. My first thought is to try spacer and see if that will get me the OD that I need. I have a lot of options on the spacer. I can do a brass shim stock. I can do plastic shim stock. But what I end up trying first is a 3D print of a spacer. And so I model it up according to the dimensions I think I need. And this will also allow me to have a single split to install it onto the pulley, as opposed to maybe having to cut it in half if I did it out of brass. So while I'm at it, and while I'm here, I also model up the pulley. Since I needed to measure it up anyway, in case I need to make a new pulley. And also, I thought of a couple of improvements. You know, some spokes in the hub instead of just an opening. It worked fine on the other one. That's not a problem, but you know, if you can improve it, I'll improve it. So first, let's print the spacer. And I'm right at the end of the cycle here. I'm using a 0.25 nozzle. I ended up with a 0.25 nozzle. I started out with a 0.4. And I still need to, dial this 0.25 in for this material, but it did pretty well. I didn't have to do much cleanup on it, a couple of little spots, but the thickness was right where I needed it, surprisingly accurate. So why 3D print this instead of just going to a piece of brass shim stock or something like that? One reason is, like I said before, a single split. I believe this is tiny. This is the size of a dime. I believe if I had done this out of the correct thickness of brass, I would kink it trying to get it onto the pulley, where I would create a small dimple. And I didn't want to do that. The other part is expansion coefficient. I'm using materials of similar expansion coefficients. It might be slightly different, but that tiny gap will allow for that. And these are the different iterations of diameters that I tried and different settings on the printer. And I made some different changes. I put that perimeter feature which simulates a straight knurl. And I also checked for outside diameter, because there is a little bit of crush and so forth on the rubber. I've got sufficient shoulder on the pulley to accommodate the spacer. Once the tire's in place, the gap will close down and it will allow, as I said, some expansion and contraction on the plastic thermal coefficient. And I'm happy with all that. Tire slips on nicely. Just have to run it around a few times and get it seated. See what kind of diameter we have here. Yeah, this is a very slippery part. It's actually hard to hold and measure and get in camera angle focused and all those things at the same time. This is a 5-second job when it's not being filmed. So that's out there at 17 millimeter, and I know that mathematically that's not correct because I've already done the math on this and I know it should be around 16.8. And now I can see that I don't have it seated fully inside of that flange. So I mess with it a little bit more. Now I've got it seated and it's apparent. Let's try to hold it for the camera and measure it one more time. That's more like it. If the numbers don't add up, there's something wrong. And those numbers didn't add up. And even though I couldn't see it properly because I was filming it, I knew there was something wrong. So I went ahead and 3D printed one of the hubs, and it's rough. I need to dial in my settings a little bit, and can also see that one of the drive pins has broken off, and that happened just while I was cleaning it up. Right there, one of them just popped right off. And that's, of course, the 3D print is not supposed to be an end product, but it's a start. So that pin broke off with almost zero force. And I remeasured everything and made a new drawing with the pins, the maximum diameter and depth and size that I could make them. And that should make a big difference. Anyway, this isn't getting the 3D printed hub or pulley. It's getting the original pulley with the spacer. But in the future, if I need to do this, I've got a drawing, I've got a spec, I know this will work, and I may have them injection molded. I don't know. All right, let's check our diameters. 1680, 81, 82 on the 3D printed part. $16.81, 82, 83 on the spaced part that will get installed in the deck. And door number 3. Right around 16, maybe a little bit more than 1671 on the original part. There's a little bit of crush there. So that's what I came up with. I know I've got a solution now in the future when this comes up. And I thank you for watching.